Welcome to the next lecture in the course Metal Additive Manufacturing. In this lecture, we will be seeing the electron beam process, the system in detail, in particular the powder feeding mechanism, because this is a very important subsystem of electron beam machining or electron beam powder bed fusion technique. The metal powder, when it is fed, the metal powder size will be approximately from 10 micron, it can go up to 60-70 micron. The biggest challenge of handling such powders will be the agglomeration. What is agglomeration? Agglomeration means the surface area is large, the volume is small, and in the surface area you are accumulating lot of charges, and if these charges are positive negative, they try to stick with each other, assuming a condition that oil or water is not present between the powders. So, we have to find out ways and means how do you dispense these metal powders without getting agglomerated. Why is agglomeration important? Because this agglomeration in turn will try to dictate the minimum wall thickness, the surface area whatever you are generating, and also defects which are produced in this metal additive manufacturing. So, we will be looking at it in detail about powder feeding mechanism. At last, we will be looking at wire feeding. Wire feeding, we cover it very quickly because the wire feeding mechanism is almost very well dealt in all of the welding courses, or this is already well known when we are trying to do material extrusion methods in polymers and ceramics. So, we will have a very small glimpse as far as wire fed systems are concerned. The content of this lecture is going to be powder feeders and their classifications. Next is powder delivery nozzle. That is a big challenge. If you can reduce the nozzle diameter further down, for example, to diameter of 100 microns, 50 microns, 20 microns, then the dispensing of the powder will be controlled in a very big manner. So, powder delivery nozzle, if it is only liquid, in combustion it is only liquid, it is straightforward. Here you have a air as well as powder. So, powder delivery nozzle will be the second one. The third one is going to be powder bed delivery and spreading system. Last, we will try to see wire feed system, then its positioning, and finally print head in this process. So, before going to detail, let us just have a small recap of all the 4 subsystems of electron beam powder bed fusion method. This is the electron source, this will be the beam delivery system, this is powder delivery system, and here is the process which is happening. The process are going to be either sintering or melting of metal powders. Okay. These are all quite common subsystems for electron beam laser bed fusion system. So, what we see in electron beam is also common for directed energy deposition method. So, the powder feeding mechanism and the nozzle which is attached to the powder feeding is almost common for these two processes. So, from now on we will try to look at powder delivery system and nozzle which is attached for directed energy deposition method, which is similar to that of your electron beam method. The most significant piece of equipment in a directed energy deposition process are the powder feeder. It is here as well as in electron beam. Okay. Powder feeder and delivery nozzle, these two are very key terms, powder feeding and delivery nozzle, which are essential to the delivery and deposition of the powder. Appropriate powder feeder is used to transport the powder during a typical powder fed directed energy deposition process, and a nozzle is subsequently used to deposit the powder onto the substrate. Whatever is dealt here may be up or down, with some modifications we use it for electron beam. The fact that a carrier gas is given to move the powders from the feeder to the nozzle should also be noticed. The powder flowability, that means to say flowing of powder, is called as powder flowability, is influenced by the rheology, physical characteristics, size, shape of the powder. Rheology means the way it is flowing is called as rheology, right. So, rheology, physical characteristics, size, shape of the powder are very important when we talk about powder flowability. Controlling the powder feed rate. So, feed rates will be, we talk about millimeter cube per minute. So, millimeter cube per minute is what is the volume of material dispersed in a minute. So, or we can try to talk in terms of millimeter cube per liter of air or whatever it is, right. Generally, we also call it in grams per minute. So, all the three terminologies are used. Whenever we talk about powder, we use this grams per minute. So, controlling the powder feed rate, which is based on the flowability of the used powder, is crucial for maintaining a stable powder stream. When the powder is flowing, you cannot have a mute zone. For example, when the powder is fed, it is not only going to be the powder and also gas will be mixed, but it will be used in a very small extent. So, this will try to focus and hit at a spot, and where you have to make sure the stream of flow is constant. In order to precisely control the feed rate and produce a continuous and homogeneous powder stream during AM operation, various types of powder feeders are deployed. So, this is used for DED, and it can also be used for electron beam method. Sometimes electron beam method also uses powder bed fusion, and in powder bed fusion you have a recoater which smears the powder from the powder container. Predominantly in DED, the powder feeders play a very important role. When we talk about powder feeder, there are classified into 4. The first one is going to be mechanical wheel or screw powder feeder. The next one is going to be gravity based. The third one is going to be fluidized bed powder feeder. The last one is going to be vibratory based powder feeder. There are many more, but these four are the most commonly used powder feeders in metal additive manufacturing. What is a mechanical wheel or a screw powder feeder? Here, a mechanical wheel powder feeder consists of a container. This is a container with a blade or a screw operating at one end. This is the screw. Screw operated at one end, varying flow rate. So, the screw speed is changed. So, the flow rates are changed. So, end varying flow rates can be attained depending upon the blade arrangement. So, you can have this as a container. This container comes down, and in this you will have a screw which keeps rotating. This will be attached to a motor. So, once it is attached to a motor, it rotates. So, the flow rate gets changed. It is an exaggerated way, but generally it will be very small. This kind of powder feeder can operate with a pressure differential between the inlet and the outlet as low as 0 and can handle powders of various size. So, that is the advantage of mechanical wheel or screw powder feeder. The powders that are abrasive can wear down the blade, rising maintenance cost. For better and more consistent result, back pressure utilized pressurized air or inert gas which will be mixed and will be sent along with the powder. The next important powder feeding mechanism is based on gravity. Using gravity for the advantage is one of the thumb rules when we try to transport material. So, lot of people always look for using gravity as their advantage. If you look into books which talk about design for assembly, disassembly, they will always say use gravity for your advantage. So, gravity based powder feeder. Gravity causes powder particles with the right flowability to pass through an orifice in gravity feeder. By adjusting the orifice area, one can manage how much powder enters the delivery nozzle. So, what does it mean? You have powder feeder. This will lead to a nozzle. So, what exits from the powder feeder and gets into the nozzle, you can try to dictate it by changing the orifice. Furthermore, external metering components can also be added to achieve the high precision feed rate. For instance, by adjusting the speed of rotating disc with hole, a precise volumetric feed rate can be achieved. For example, if you have a 2-plate system, so this is one plate where there are holes, you can have another plate where there are holes. Now, these are plates, plate 1, plate 2. So, these plates will be stacked one above each other. This is plate 1, this is plate 2. So, now what will happen? You try to rotate it in such a fashion such that you can have a precise volumetric feed rate. Based on the idea, other components of a similar nature. So, here what happens? This will rotate, you can keep this as stationary. Okay. So, every time you can try to control the whole alignment and then you try to get. Based on this idea, other components of a similar nature have been created, replacing the rotating disc with a metering wheel or a lobe gear. So, this is how it looks like. So, you will have gas which comes inside, then you have a hopper where you have the metal powder. So, now this has an orifice. This orifice is connected through a nozzle to a plate on the top. So, this plate rotates, okay, and the other end you will have powder which is getting ejected. So, the gas pressure is also important. Then here you will have the hole diameter. The hole diameter is also important, hole diameter, because that dictates the amount of or the volume of the metal powder. Use it like this, or you can think of using it like this. So, this is another schematic diagram of a gravity based powder feeder with a metering wheel. So, you can have something like this. So, you have the air gas which goes, generally we try to use inert gas, it goes inside a hopper where they create a back pressure. So, this abrasives or the metal powders flows down, and here what happens is it is placed in a shaft where this shaft is attached to a roller, and this will try to rotate. So, you have bearings, shaft, and this will rotate, and once it rotates, the other end you will have a orifice. So, this orifice tries to push the abrasive down. So, you can see here this gas is used for back pressure. This gas is also used for making sure that the metal powders, whatever it flows, try to get spread on top of a powder bed. Okay. So, this powder bed or on a substrate where you want to go. So, this is the second type of gravity based powder feeder used in directed energy deposition method. The third one, which is gravity based, I would prefer to use gravity because gravity is such thing which comes free of cost. So, you do not have to pull or push something, it falls of its own. So, the other way around is we have a gravity feeder with a lobed gear. So, with a lobe gear, so you will have powder feeder. This powder feeder is or the container, and here you attach it with gas, and then you also connect it directly with the nozzle exit wherever it is. So, here what happens, the abrasives or the metal powder gets accumulated, and this is rotated. Once it is rotated, when it comes to an exit orifice, it tries to exit out, and the metal powder is fed continuously. So, this is metering wheel which tries to control the flow. The next classification of powder bed feeding system is going to be fluidized bed powder feeder. So, here what happens, we will try to have a back pressure which is created, and then this passes through a hopper where there are two stoppers. This goes, the metal powder flows like this, and you will have a gas injecting point. This will try to inject gas, and you try to allow the metal powders to pass through this stopping and enter through the hopper. This through the hopper or through the orifice, it comes and deposits onto a plate or a substrate, and you can see carrier gas is also fed here, so that the powder can move along with the carrier gas. So, fluidized bed tries to give a more controlled fashion of powder feeding, and here all the humidity and other things are removed nicely because of the involvement of fluid. Fluid is nothing but air. Based on the patent discovered from the fluidic principle, the fluidized bed powder feeder was created. Fluidized bed powder is exhaustively used for coating of tablets. Fluidized bed is exhaustively used for heat exchange or for removing humidity. All these things, fluidized bed is effectively used. The benefit of this powder feeder is that it does not use any mechanical component to deliver the powder, which lowers the cost of upkeeping and part replacement. So, if there is a wear and tear in the powder feeder, then the amount of material which is getting dispensed will not be controlled. So, your quality of the output is a big difficult task here. So, fluidized bed powder feeder are very much used, because here it is predominantly air tries to drive it. A very high coating quality is guaranteed by the uniform and continuous powder stream. A specific volume of gas is delivered to a closed hopper that contains the powder as a basic operating principle. So, if you go back, this is what is we are talking about, a gas which is injected where the powder is flowing. A filter at the bottom of the closed hopper diffuses the gas through the powder, fluidized it. A pickup tube and a carrier gas are mounted on the top of the unit to deliver the fluidized powder under a shed and to feed hose respectively. So, this is the all about fluidized bed based powder feeder. The last one which we will see is vibratory based powder feeder. It consists of a tray that oscillates at 50 to 60. So, this is 50 to 60 hertz vibration happening. So, the volume of the flow of the powder can be indefinitely adjusted to ensure a steady state powder flow as it moves from the hopper to the vibrating tray. So, here it is vibrated, these are all constants. So, from here it gets dispensed and then falls on a tray. From a tray it gets into the plate wherever it is. For better control of powder flow, some vibration bed powder feeders have an oscillating tray with various plates arranged at various angles. So, what I showed you is a very trivial one, but in reality you will have various plates and various angles. With plus or minus 1% accuracy, the vibratory bed powder feeder can feed a variety of powders at speeds from 8 grams to 2000 grams per minute. It is very high, 2000 grams is 2 kgs per minute. So, now we will move further and we will see in directed energy deposition powder delivery nozzle. The interaction of the powder particles with the laser beam, melt pool and unmelted surface during laser directed energy deposition are essential for the quality of the printed part. The interaction of powder particle with the laser beam. Here if the flow is very high, the laser spot diameter is low, it moves very fast, you will not have a proper diffusion. Melt pool creation and unmelted surface during LDED are essential for quality of the printed head. The type of nozzle, the angle between the powder delivery system and the deposition plate, the diameter of the powder stream all play a very important role. First is nozzle type, the next one is angle, third one is diameter of nozzle, and fourth one is the plate deposition. All these things are very important. To ensure that the manufactured part are of high quality, the appropriate nozzle has to be chosen. It depends upon the material and the manufacturing process. The delivery nozzle, so hopper and then you have a attached is the nozzle. So, the delivery nozzle can have two different configurations, one is lateral, another one is coaxial. This is what is very commonly used as lateral nozzle. In lateral nozzle what happens, there will, so here you have your hopper, this is your hopper, all the powder feed system what we saw, it is all here hopper. So, then it gets into a nozzle. So, this nozzle tries to feed the powder at the substrate where the laser is focused. Okay. So, the lateral nozzle, this is lateral to the laser. So, it is lateral nozzle. The powder is delivered from the side in the additive manufacturing process when a lateral nozzle is used, and an inert gas that passes through the nozzle aids in the powder delivery stream while preventing deposit oxidation. So, here the lateral nozzle is used and an inert gas passes through the nozzle. So, here it will be two flow. So, one is flow of metal powder, and this will be driven by a gas. So, this gas tries to prevent oxidation happening at the laser matter interaction. The lateral nozzle reliance on trajectory orientation is one of the problem. The way the powder stream interacts with the melt pool will change if the lateral nozzle is fixed to the laser beam axis and the trajectory is not linear. When you have untoward surfaces like this, so then the way the powder stream interacts with the melt pool will change if the lateral nozzle is fixed to the laser beam axis. So, if these two are fixed, if this and this are fixed, then you will have this lateral nozzle is fixed to the laser beam axis and then the trajectory is not linear. Due to this problem, some business include Optomech have created a nozzle that has 4 lateral nozzles. In lateral nozzle, we will try to see some little bit of science. As was mentioned in the previous section, the powder delivery system has a significant impact on the quality of additive manufacturing produced parts in terms of powder stream diameter. So, at the orifice of exit it is called as D naught, at the profile it is called as D, D naught, D, and the standoff distance is called as Z. Okay. These three are very important. So, the powder delivery system has a significant impact on the quality of the part produced. So, the powder stream diameter that must be deposited, the stability of the powder feed rate, the speed of the powder particles and the uniformity of the powder profile shape, all these things are very important. So, the D, whatever it is which we see the D at the substrate where you have to deposit the material, you can find out that in terms of height and nozzle diameter. The powder stream profile could be described by a parabolic equation. Why parabolic? It will go something like this. Parabolic equation, this is the powder feed. Depending on the distance, it gets dispersed. It has to be something like this. Now, it gets dispersed. The laser stream profile could be described by a parabolic equation according to research done using a different nozzle with different diameter. So, this is directly proportional to the Z square. Z square is the distance D naught. D naught is the profile diameter at any Z. Lambda is the powder profile quality coefficient 1 by millimeter square. It is valid for a particular range when the powder stream is stable. D naught is the nozzle diameter, Z is the distance between the tip and the nozzle. When we try to talk about coaxial nozzle, coaxial means you will have 2-3 nozzles coming out. So, you see here, here is one nozzle, here is one nozzle, they are coaxial to the laser. Coaxial nozzle has the same deposition rates in either directions and greater powder efficiency. Same deposition rate in either direction and greater powder efficiency as compared to that of your lateral nozzle, which is the ratio of the powder deposited on the workpiece to powder provided by the powder feeder at a particular time. A lamellar powder stream at the nozzle outlet delivers a homogeneous powder stream and a high quality product, a lamellar powder stream. Maintaining this is a tough problem. Next is focusing on the melt pool ensures optimum part quality and the part efficiency. What is melt pool? When the laser hits, so what happens is you will have some amount of melting which happens. So this is called as the melt pool. Okay. So nozzle outlet delivers a homogeneous powder stream and a high quality product. Focusing on the melt pool ensures optimum part quality and powder efficiency. Choosing the correct nozzle tip can create lamellar flow, powder stream pattern and powder focus. Like you had your TEM10 mode, here also what happens when you have these nozzles, you can start playing with it. The powder stream is shaped by a parabola, same thing like your astigmation, we are talking about a parabola. Unlike a lateral nozzle, the powder stream converges and then diverges. So what they say, converges and then diverges. So you have to find out what is it. So this is called as the, so it's focused and then it diverges. So the powder stream at the nozzle exit of your coaxial laser. So you have to place your substrate here, 20 to 100 micron layer substrate location. Okay. So these are coaxial nozzle. If you see here, it is only 2 because it's a 2D. So if you have in reality, what will happen? You will have all around the periphery, you will have 1, 2, 3, 4, 5, something like that. So you have a laser, so shielded gas, then you have nozzle. Through this nozzle, you will try to have this powder fed coaxially to the workpiece and then you do it. Here also we try to use gas. So this gas purges on top of it and then it tries to do it. See, all these freedoms are possible in laser. In electron beam, you don't have this shielding and other things. You just have to do it in vacuum. Now we are moving into the next section where we talk about delivery and spreading mechanism. So in powder bed process, a roller, wiper slash recoater or a doctor blade compacts of metal powder over the built region. A laser beam melts the first layer of the powder using computer generated path. After the first layer scans, the built platform descends one layer and one powder layer is spread by using the spreading mechanism. The powder delivery system must maximize powder flowability, reduce particle clustering and minimize shearing force. The powder bed fusion is a complex process. So it's important to have a homogeneous powder thickness in each layer, because whatever powder gets fallen down, it has to be spread. It has to be spread by a doctor's blade or by a recoater to maintain the uniform thickness. And in one layer also, you should have, say for example, when we try to have a powder and then you will have lot of flea places. So that also has to be optimized such that we get a good quality output. The inert gases are introduced into the metal chamber to prevent oxidation of the melt pool and remove condensate. So melt pool I have already told. During this melt pool, it is always a possibility of attracting oxygen and the oxygen gets diffused into the melt pool. We try to avoid it. The density of laser powder bed fusion parts depends on the speed of the counter rotating roller, roller properties, powder lead layer thickness and powder particle size. All these things try to dictate the powder quality. Trial and error techniques, mathematical modeling and simulation provides information on the compaction phenomena. Recoater can be a soft or a hard blade or a roller. Both spread roller particles evenly, but their interaction are different. Such differences affect the compaction density of build chamber powder which affects the additive manufactured part. Silicon, rubber or soft carbon fiber are often chosen for soft recoaters. Due to its stretchability, soft recoaters behave well in additive manufacturing while building parts. So, these are the recoaters. Main tank, hopper. So, what they do is these recoaters move on top of it and it tries to coat a very small thickness. They also make sure that there is the powder particles are kept close to each other and the space between is optimized such that when the laser hits, it melts and it does not generate any porosity there. So, previous layer you can see initial plate, then spreading of powder has happened. This is a recoater. We use argon gas to make sure oxidation does not happen. This is a laser, this is a scanner. So, this is what is a limiting unit, because mechanically it has to sweep on a floor and then get. So, these are all the melt zones, and by the way this is one layer. In one layer you see islands of hatch patterns are created for generating a good quality output. The type of recoater may be ideal for concurrent additive manufacturing of different parts in the same built chamber. Hard coaters made of high speed steel or ceramic exerts pressure on the powder bed. Unlike soft, this type prevents part deformation. So, hard and soft recoater, it of two types, soft and hard. So, hard means it will, there is a possibility that you can have somewhere non-uniform spreading, but whereas in soft you will always have uniform spreading. When a recoater collides with a warped part, it jams or parts are separated from the support structure and drags across the powder bed. So, we will always try to avoid using it. So, this will crack and break the part even hard. So, that is why we always go for soft recoaters. So, the recoaters are useful when printing identical parts on a same platform. It may also increase build chamber compaction density and improve quality. Paralleling parts to the recoater can cause jamming. Paralleling parts to the recoater can cause jamming. For better recoater force distribution, there should be oriented around the Z axis. So, this is also an important point which you are trying to do. And here when we are trying to do in additive manufacturing, we can also have various parts simultaneously getting built and then you detach, then you try to do an assembly. So, this is what we are trying to talk about when printing identical parts on the same platform. 1, 2, 3, 4, 5 are identical. You can have 1, 2, 3, 4, 5 are different. It may also increase the build chamber compaction density, improve quality. The last process which we are discussing is going to be wire fed system. In directed energy deposition additive manufacturing, a solid wire feed stock, powder can also be used, wire also can be used instead of metal powders. Why? Because of this all the problems of agglomeration, not improper feeding, we converted into a wire. Wire can be easily extruded. So, the feed stock capturing efficiency is 100% in wire feed system, and the deposited volume is the same as the feedstock wire. Powder fed / bed and wire fed processes have these features. So, they almost have the same feature like that of the powder. Wire fed electron beam fusion method EBF has a much higher deposition rate as compared to that of powder bed. However, fabricated parts are less precise when we use wire as a starting material and even though you use electron beam. In additive manufacturing, machines with wire feeder are simple and complex geometries can be easily achieved. However, the later requires the complex shape requires a careful control of the process parameters, and it is not possible to obtain simultaneously high geometric accuracy and powder as a starting material and wire as a starting material. This is a very important point. So, please make a note. Okay. Wire based direct energy deposition machines are used when pore free parts and dimensional accuracies are not important criteria of making additive manufactured part. Depending upon the energy source used, wire feed additive manufacturing can be laser based, arc welding based or electron beam based. Electron beam fusion is promising for aerospace application because it can be done in vacuum. The wire also can be done in vacuum. It is equipped with wire feeder, avoiding the use of powder and then powder spreading difficulty. So, now here let us compare between layer thickness, deposition rate, dimensional accuracy, surface roughness with powder can be used for laser cladding. You can try to have layer thickness from 100 microns to 1000 microns. Deposition rate will be 1 to 30 grams per minute. Dimensional accuracy will be 50 to 500 millimeters plus minus. Surface roughness will be 5 to 50 RA microns. Then when we talk about powders as a starting material, laser powder bed fusion, you can have a layer thickness of 20 to 100 and deposition rate is not applicable here, and dimensional accuracy what you get is plus or minus 25 and the roughness can vary up to 10 microns. When we talk about selective laser sintering method, the layer thickness can go from 50 to 75. The feeding mechanism is not there because it tries to spread by a recoater. The dimensional accuracy can be up to 10 millimeter, and here you will try to have the surface roughness from 14 to 16. When we talk about directed energy deposition, here the layer thickness can vary from 100 to 1000. The deposition rate will be 12 grams per minute, and then dimensional accuracy will be plus or minus 25 to plus or minus 500 microns. The roughness will be approximately 20 microns. When we talk about arc welding, so this is all done as far as powder, and here we have direct energy deposition, arc welding and electron beam. So, here you can have arc welding, which is around about 1500 microns will be the layer thickness. The deposition rate will be 12. The dimensional accuracy is almost the same of DED and the roughness goes very high up to 200 microns. When we talk about electron beam, the layer thickness is for wire it is not applicable. Then it can go up to a deposition rate of 300 grams per minute. The dimension accuracies are extremely low here and the surface roughness is very high, more than 200 microns. So, through this table you are able to compare with respect to starting material whether it is a powder or a wire, which process to use, what are all its performance with respect to various process parameters. So, this is a wire fed system. So, you have a wire which is getting fed here, a laser which is getting hit here, or an electron beam. It says electron beam. So, you can also have electron, this is a beam, then molten pool. So, this is the alloy which is always called as melt pool. Okay. This is molten alloy puddle. Then you will have prior deposition. So, this is prior deposition and this is substrate. So, you are trying to the previous layers. So, this is resolidified alloy. This is how the wire is fed, and here you will have the spool and other things. So, this is the direction of the part. So, the gun can move up and down x and y. So, it can move in the x direction, it can move in the z direction, or it can move in the y direction. So, this type of additive manufacturing, that means to say wire fed systems, can have lateral or coaxial wire feeding mechanism, just like your powder feeding, which can be lateral and coaxial. The second setup is omnidirectional. The laser is split into 3 beams and focused on a circular focal point. We are now trying to play with the laser. So, the laser beam is split into 3, and then all these things get focused on top of a substrate. This is your substrate. Okay. So, this is a laser. So, the laser beam is split into 3 beams and focused on a circular focal point. The optical element's precise location centers the wire feed in the laser beam. This configuration allows the wire to be fed in the center of the laser generated melt pool. Contact forces must be kept constant to ensure additive manufacture produce a good quality output. This technology cannot make complex parts with respect to wire frame, because the wire itself, when it gets melt, it will not be very small particles, it will be a large droplet. So, complex parts cannot be made through this. So, this is what is the laser which I said, you are splitting it and you are trying to focus it. So, this is a flux core wire feeder, then you have shielded gas which is there, then you have a coaxial wire optics, then laser beam, 3 laser beams, it tries to hit at a surface. So, shielded gas flux coat wire is there, and then hard facing are getting deposited. The last part of our discussion with respect to different systems is going to be the positioning device. In additive manufacturing, machine makes parts for various use. The size, shape and the machine all tries to depend on the positioning. Positioning tries to dictate the quality of the output. Due to workspace constraint, what is workspace constraint? This is a workspace, so within which you start developing the output. So, here is the table. So, this is the workspace. The workspace constraint the size and the shape of the object to be printed. CNC and robotic arm are used to handle the material delivery for wire in a big way. So, when you use a 5-axis robo, it tries to generate a complex surface. Complex surface means a very curvatured surface, but the accuracy is poor. The positioning device should provide workspace, speed and acceleration for the building of parts. Positioning devices are connected to the controller that determines their movement, trajectory, speed and acceleration. The laser powder bed fusion galvanometer scanner positions X and Y, which is a positioning device. The galvo system consists of a galvo motor, 2 mirror controlled by a motor and a servo drive board. Multiple coils in a magnetic field forms a galvo DC motor. So, positioning is very important. When a galvo motor senses an electrical current flow through a coil, it generates a torque proportional to the current while deflecting the laser beam. This is very important, electric current flowing through the coil which generates torque, and this tries to deflect the laser beam. The precision position detector on the shaft measures the mirror angular position for a closed loop system. We can also use open loop system which is economical, but you have to compromise your quality. So, this is what is the galvo. So, this put together is called as a galvo system. You have a X galvo, Y galvo, then it passes through F theta lens which tries to give you a focus anywhere on a single plane. So, this is the working distance, this is the X mirror to lens separation, this is the XY galvano separation, and this is the X separation. This is a positioning device which is exhaustively used in laser. So, points to ponder: in this lecture we saw how are powder getting feed, how are wire getting fed, and how is it happening through a nozzle. We also try to see the positioning device which plays an important role in generating a good quality output. So, here I would like to give assignments. The first assignment is going to be try to understand the wire feeding mechanism in arc welding or in fuse deposition. How is it controlled by a controller by touch of a button? So, that is one. Second thing is, if you can start looking into a wire feeding mechanism which is used in your tailoring machine. When you start moving the pedal, you can see the wire or the thread which is getting forced, which feeds continuously. try to understand how is a tailoring machine works. That means to say, in particular, thread getting fed. If you see that, you will try to understand and appreciate the complexity involved in wire fed mechanisms. And also you can look at how are the CAD file formats and different softwares which are used in accommodating powder feeding, delivery of the nozzle and wire fed systems. The assignments which are given in the previous lecture you can add. Make a list of advantages and disadvantages of using electron beam. Also make a list of different types of nozzles used in the powder bed fusion process, stating their advantage and disadvantages. With this, we are coming to an end about the basic understanding of the processes. Thank you.